Hi everyone. Today I would like to present our work, Blink Toward a Real-Time Convolutional Neural Network Approach. This is joint work with my co-author from UC Davis, Rex, Rahul, Vishal, Xiaoxiao, Professor Ilias Tagkopoulos, and also my advisor Professor Shin Lu. My name is Albara Ramli. I am a PhD student at UC Davis. So I will start with introduction, then system implementation, training models and results, demo, and conclusion. A number of clinical conditions, such as brain trauma and ALS, causes damage to the central neural system or brain, so that the ability of speech and motor functions cannot be sustained. In those cases, the ability to communicate is limited to non-verbal form of communication, such as eye blinks. To start off, it's perhaps well known that many popular image recognition methods have hard time learning certain tasks, especially those with sharp angles and poor light conditions. To avoid these shortcomings, we here present a deep learning vision system that detects eye blinks and map them to word in real time. Our system achieves an accuracy of 99.2% with a latency of 94 milliseconds on IoT devices. Our method is safe to use and has better performance than previous methods. It's robust to changing in light condition and facial orientation. The architecture is modular, so its output can be mapped to not only word but also other tasks such as controlling software application or devices. Here we present an artificial intelligence system that uses eye blinks to communicate with the outside world, running on real-time IoT devices. The system uses a convolutional neural network to find the blinking pattern, which is defined as a series of open and closed states. Each pattern is mapped to a collection of words that manifests the patient's intent. System implementation. The system is divided into three phases as shown in this figure. Phase 1, capturing and saving a stream of frames. The system uses a camera device attached to IoT for capturing the frames. Our experiment shows that 10 frames per second are a reasonable frame rate for the real-time application. Phase 2, predict the content of the image. Choosing the best fitting neural network architecture to predict the states of the eyes was the main goal of this phase. We compare 4 state-of-the-art architecture and we chose the best one. Phase 3, mapping. Our system stored the output of the neural network as a vector of zeros and ones, where zeros represent the open state of the eye and 1 represent the closed state of the eye. The system provides a special word to start and end the session of blinking, which is keeping the eyes for 4 seconds will start and end the session, and the system will recognize the end of the word when the patient remains open 1.5 seconds or more. Based on the output vector, the number of blinks is calculated and is mapped with the word in the dictionary. The dataset contained about 84,000 images of eyes taken from 37 individuals, consisting of 33 men and 4 women. The dataset contains 6 different characteristics, such as genders, glasses, eye state, reflecting, light condition, and sensor resolution. We split the dataset into an 80% for training set and 20% for test set. To investigate the best trade-off between accuracy and latency, we investigated several convolutional neural network architectures such as ResNet, SqueezeNet, DenseNet, and Inception version 3, and we evaluated their performance. We trained different architecture with different hyperparameter to identify parameter combination that lead to high accuracy and low latency. For the sake of conducting a clear competitive analysis, we compared the result of each architecture with different batch sizes such as 8, 16, and 32. Our goal is to find a neural network architecture that is optimal in terms of accuracy and latency. We created a system that is safe to use and works in real time at the same time. Our goal represented by this following equation, where P refers to the performance of the system, which is in our case the accuracy. S refers to the system parameters. W refers to the weight of the neural network. A refers to the architecture. H is the set of all architecture that can be used for this purpose. T refers to time constraint, which is the prediction time or latency. It's important to reduce the response time of the system since it will be running over a real time on IoT devices. We divided our data into 3 subsets: training, validation, and test set. We trained our model on the training set and then we evaluated it on the validation set. We used the validation set to measure how well a model generalized to unseen data. So first architecture we used was ResNet. ResNet is one of the art of the state architectures. We trained our ResNet model from scratch. Take a 16 batch size number as an example. It took 55 epochs to stop before overfitting. This table presents the result after training the model for 100 epochs. As you see here, the batch size 16 gave us the highest accuracy of 99.26. For batch size number 16, that gave us the best accuracy in ResNet architecture, here is the accuracy curve in left and loss curve in the right. During training, the samples are split into 2 internal subsets, one which is used for actual training and the other used for validation after each epoch. The red curve is validation, out of sample. The green curve is training, in sample. To avoid overfit, we stop at epoch number 55 at the blue line. Then we implemented other techniques such as training, transfer learning in order to discover the neural network that is heavily optimized accuracy. The rule of transfer learning was to speed up learning and boost the performance of our model. We run ResNet for all batch size for 500 epochs. The result shows that there is no further improvement in accuracy. Then we introduced transfer learning, which improved the conversion when compared to random weight initialization. We used transfer learning in our research in order to improve our model accuracy, but it didn't surpass the model that was trained from scratch. However, we find that transfer learning speeds up the learning and training process. The transfer learning uses less time to get good results, and it helped to speeding up the learning process, but it didn't necessarily guarantee a high accuracy. On the other hand, DenseNet reached accuracy of 99.24, which was at the batch size number 8. Here is the accuracy and loss curve. In case of SqueezeNet architecture, it didn't get any good accuracy, no matter what is the batch size or epoch number. The accuracy is less than 50%. The architecture was too small to learn. Here is the accuracy and loss curve. Finally, Inception version 3 architecture got an accuracy of 99.2% with batch size number 16. The accuracy here is less than what we got before from ResNet and DenseNet. At batch size number 16, the model start overfitting from epoch number 22. Best accuracy before fitting was 99.2%. Here is the accuracy and loss curve of batch size number 16, the one that gave us the highest accuracy in Inception version 3 architecture. The red curve is validation out of sample. The green curve is the training in sample. To avoid the overfit, we stop at epoch number 22. The elbow here is very clear. SqueezeNet received the lowest accuracy with the fewest parameter. The DenseNet, ResNet, and Inception version 3 acquired accuracies in the range of 99.2 and above. So far we tested all the architecture and we get all the results. We made this final comparison among the best result obtained from different architectures. Apart from the accuracy of the network, this table also contains the time required for prediction or latency of each image for different architecture. We can see here that the ResNet has best accuracy but has a high latency, which is 117 milliseconds. As Inception version 3 had the lowest latency, which is 94 milliseconds, and good accuracy, which is 99.2%, we choose this architecture to predict the state of the eye. Demo. Here we will ask two questions for a person and he will reply by blinking. The system will convert these blinks to actual text. The first question is, how are you? The person will respond, I am good. The second question is, do you need any help? The person will respond, no, thanks. Let's see the demo. Here we ask the person, how are you? And here he's replying using eye blinks. He said, I am good. And this is the pattern. Now, do you need any help? The person will respond using eye blink as well. He said, no. He said, no, thanks. Conclusion. In this work, we designed an AI system for nonverbal communication that convert eye blinks toward using deep learning CNN architecture. The system predicts the state of the eyes of the patient and find the blink patterns. We compared several CNN architecture and hyperparameter selection in model training. For the evaluation, we tested our system using about 16,000 image eye and found that our proposal prediction model was efficient and effective. Results demonstrate that overall prediction accuracy is 99.2% and the average prediction time is 94 milliseconds. Thank you.